The broadcast is now starting. All attendees are in listen-only mode.
Hello all, I'm Steve Clark. I'm the Secretary for CMG and I will be your moderator today. This webinar is sponsored by ThruPut Manager, the premier batch automation software product for ZOS and JES2. It simplifies the data center environment and provides better service to users with minimal operator intervention. ThruPut Manager improves resource utilization and system throughput, delivering more work using less of the batch window. CPU upgrades can be deferred and software costs can be reduced for year-on-year savings. ThruPut Manager is tightly integrated with ZOS, giving it the right level of system information and control to truly automate batch management. Presenting today is John Baker, Z Performance Specialist with over 20 years experience as both a customer and consultant. John has spent 15 years specializing in mainframe performance at a large international bank and 6 years in enterprise I/O performance with IntelliMagic. As a customer, John designed, implemented, and maintained many critical projects such as WLM Goal Mode and GDPS data mirroring. He has extensive experience with many performance analysis tools and techniques at the hardware, OS, and application levels. As a consultant, John has assisted many of the world's largest data centers with their ZOS performance challenges and held subject area chair positions with CMG for both storage and capacity planning for several years. John has hosted many sessions at CMG and Share, as well as several regional CMG user groups. In 2013, John joined MVS Solutions as their principal Z Performance Specialist and ThruPut Manager product expert. You will be in listen-only mode throughout the presentation. Questions during the presentation may be asked using the chat box on your GoToWebinar screen and will be relayed to John. And with that, John, all yours.
Thanks, Steve. That's quite an introduction. Thanks, everyone, for attending. We're really happy here to be partnering with our friends at CMG. Look forward to seeing you all in November down in San Antonio. But let's get into this. By now, we should all be collecting Type 113 SMF records. These records are collected by the CPU measurement facility rather than standard RMF. There's lots of good presentations out there about how to collect and interpret this data. But today, I want to talk about some practical actions we can take to improve relative nest intensity, which I'll explain in a bit, and overall performance. The agenda will cover why you should care about analysis of memory performance, the 3 major factors in workload capacity performance with a focus on memory use. We'll talk specifically about how memory is used in a mainframe and even how you can improve your MIPS rate and prove it to your boss. We'll get back to this in more detail later, but just to level set, this is the basic layout of the Z13 processor caches. The processors are at the bottom in red, and they're connected to the various cache structures as indicated. When you hear the term the nest, this is the area that's being referred to, specifically the caches that are not physically on the processor cores. The 113 records report on all of these areas, counting instructions, processor cycles, and relative time spent in each tier. This information provides a very detailed profile of your relative performance and efficiency. So why do I care? RMF has given us excellent performance and capacity stats for years. Memory's cheap, processors are fast, and we're already measuring CPU time. So why would I go to the trouble of measuring system performance at this level? Well, let's talk about memory. Memory has steadily become bigger and cheaper over the years. We know this intuitively in our daily lives, where we once had PCs with kilobytes or megabytes of memory, we now have gigabytes. Take your USB thumb drives, which are essentially nothing more than flash memory. They've grown at the same scale and are now cheap commodity items. Even PC and tablet hard drives are being replaced with solid-state drives. These are also based on flash memory. In the mainframe world, The Z13 offers up to 10 terabytes of main memory. 10 terabytes. I'm still wrapping my head around that one. So back to the question. This chart shows the relative improvement in CPU performance versus memory performance over the last 30 years. The Z13 processor runs at 5 gigahertz. That's 5 billion cycles per second. The EC12 actually runs even faster. As you can see though, memory performance has not kept pace with Moore's law of CPUs. In short, while memory has gotten bigger, it hasn't gotten much faster. Now to understand what this means in a mainframe environment, let's consider what the Z13's 10 terabytes of memory would look like in the real world. Yeah, now in this diagram, you are the CPU, and your car is the next instruction that you'd like to execute. Well, first you need to go get that instruction from memory, right? As I mentioned in the last slide, the CPU may be spinning at 5 billion cycles per second, but the memory is significantly slower. On the left is an illustration comparing the parking lot to the various memory tiers in a computer. Now we'll get into this in more detail later, but suffice to say that while that instruction is being fetched, the CPU is unproductively spinning away. Which brings us to our next point. I love this old joke. If a 3 gigahertz processor is waiting for a cache miss and a 5 gigahertz processor is waiting for a cache miss, which CPU waits faster? Of course, all CPUs wait at the same speed. Now this has always been true, but the issue is even more important with today's high-frequency processors. It's like a chain with the weakest link. In order to realize the performance gains from a faster processor, the rest of the infrastructure, in our case the memory structure, must be able to feed the CPU fast enough. Otherwise, your shiny new CPU will be spending a lot of time waiting. Now, speaking of unproductive time, let's talk about the costs of waiting. Now imagine if the taxi rate was entirely based on your time spent in the cab, rather than the distance that you traveled. This is the basic method of charging by CPU time, which is the most common method in use today. Your bill for using the CPU is primarily based on the length of time that your task holds the CPU, not your instruction rate. So less efficient workloads are not only slower, they're also more expensive. Now all of this is essentially to argue that raw CPU speed is no longer the defining factor in overall workload performance. Notice here that the Z13 is actually slightly slower than its predecessor, the EC12s, in terms of clock speed. Now there is an estimated 12% improvement in performance. This is primarily due to efficiency improvements and features such as simultaneous multi-threading and single instruction multi-data. Now features like these certainly improve the overall performance of the machine, but they do little to solve the problem of the lone waiting instruction. Now let's just switch gears here and talk about performance in your mainframe. When I started the research for this presentation, I went back and read the LPAR doc again. Now, if you're not familiar with the Large Systems Performance Reference, this is the fundamental methodology that IBM has used for many years to measure and rate the relative capacity of all of its mainframe machines. Now, to understand how the relative performance of your workloads is determined, I would really encourage you to review the section on LPAR workload categories. Now don't worry, it's nowhere near as painful as reading, say, the POP manual. It will be your dreaded principles of operation that you subject your new trainees to. Now here, we're just going to touch on the three major factors in workload performance: instruction path length, instruction complexity, and memory hierarchy. Instruction path length. Now, as the name suggests, Path length refers to the accumulated number of instructions to complete the task. It's a little bit like counting the number of words that are required to explain a point. My wife happens to be very proficient with language, so she can generally make her point in fewer words, often just a look actually, whereas I'm sometimes guilty of being rather verbose. Now in the mainframe, a simple example is a transaction that deposits money into an account. The basic instruction at the CPU level could be add the contents of register 5 into the contents of register 6 and store that result in register 7. You could think of this as the application path, which can only change if you change the application. But it's not that simple. The application will need services from ZOS. JES needs to schedule the task and manage the output. Catalog is likely going to be called to look up the location of needed data. iOS will be called to perform the actual IOs to external storage and so on. So these services and more in ZOS are shared with all of the tasks in the system. What this means is the machine path length will increase with the number of concurrent tasks and the number of concurrent processors. Now, rather than counting the number of words, instruction complexity refers to how, say, difficult the words are to translate. The machine understands a basic instruction set. Technically, it's a complex instruction set in ZOS. Some instructions are more complex than others. Now, at the end of the day, there's not much to be done in this area. Application performance as it relates to instruction complexity is primarily based on the speed of the processor. And as we have already discussed, processor speed is not the real challenge here. Now, the third major factor in workload performance, and the area we're going to focus on, is the memory hierarchy. This refers to the caches and data buses that move data and instructions to and from the CPUs. Now, some caches are dedicated to a CPU core, and some caches are shared among CPUs. As I mentioned earlier, when you hear the term the nest, that's referring to the shared caches in an IBM mainframe. Now let's take a closer look at the Z13 layout. Now the Z13 has a lot of real estate. Like its predecessor, the EC12, the Z13 has 4 levels of processor cache plus main memory. This diagram is taken from the Z13 Redbook. Shows the basic memory layout in a single drawer. The level 1 and level 2 caches at the bottom are physically located on the CPU chips, providing very fast access to data. Levels 3 and 4 are larger and shared among multiple processors. Now, when you hear the advertised 10 terabytes of capacity, this is derived from the main memory module shown at the top here. So a fully populated Z13 has 4 drawers, each with 2.5 terabytes of main memory. Now, cache structures are designed using a couple of principles. One is the idea that data that is referenced once is likely to be referenced again. The other principle is a concept that other data that is close to the reference data may also be used. Now, this second principle is referred to as locality. For these reasons, when data or instructions are fetched, an entire cache line is fetched, rather than just the individual instruction or data record. In the current Z architecture, a cache line is 256 bytes. Now, as data is continuously fetched, the caches fill up, and something has to give. To make space for new data, the oldest or least recently used cache lines are discarded. Now, LRU is a very common method that ensures that data that is most frequently referenced is most readily available. It's kind of like short-term versus long-term parking at the airport. The cars that are constantly in and out are parked closest to the terminal, whereas those that are not moving very often will go to the back of the lot. Now remember that parking lot picture? With memory, as with most things, there's no free lunch. You can have cache that's big or fast, but not both. The reason systems have multiple levels of cache is to reduce latency. Latency refers to the time that the CPU has to wait while data is fetched from the various cache levels. This is typically measured in CPU clock cycles. So imagine in this picture an older system that had no local caches but had to go directly to main memory. The latency required to travel through all the system bus and then search through a large main memory would mean that your fast CPU is just spending more time waiting for work than productively executing instructions. Now, given that the cache areas of concern are those that are not physically located on the CPUs, IBM introduced this concept of the nest to refer to those shared cache areas. This idea was hatched, pardon the pun, with the Z10. The term relative nest intensity was also introduced to provide a method of quantifying the degree of activity within the nest. The higher the RNI, the higher the activity to the nest, and the lower overall performance. The lower the RNI, the better the performance. Now, because cache structures are slightly different with each machine model, the RNI formulas are also slightly different. The Z13 formula is here on the slide, but all the other formulas are available on the LSPR website listed at the bottom of the slide. And don't worry, I'll have that link at the end of the presentation if any of you miss it. Now this table is taken from the LSPR doc as well. One of the main points that IBM makes is that many of the factors that affect RNI are simply out of our control. Generally speaking, applications are what they are, the flavors that they exhibit and what have you. What I'd like to talk about are the factors that we can control. So let's just step through a few of these. Okay, what if we just run batch? All right, maybe not a practical option, but this partially explains why systems that primarily run batch versus systems that primarily run online show better RNI values. If you want to get the most out of your batch by fully automating, you're probably running ThruPut Manager, but that's another webinar. Now, if you've been in performance for any length of time, you're familiar with the old mantra, the best I/O is no I/O. While we've always known this to be true for application performance, this shows that reducing I/O can improve your RNI as well. So get in there and tune those applications. Buffers are free. Now, application mix refers to the number of diverse applications you choose to run on an LPAR or machine. It's rarely practical to dedicate an entire LPAR to a single application. The lesson here is to not mix any more applications than your business requires. Different applications will likely access different data sources. If you remember those previous points on cache lines and LRU, the more your system can access the same data, the more responsive it will be to your applications. Now these three factors, CPU usage, dispatch, rate, and data reference patterns, these kind of fall into the not much I can do about it category. They're basically native to the application. But here, on the other hand, is another area where we can do something. LPAR configuration refers to the number and complexity of the LPARs on a given machine. The Z13 allows up to 85 LPARs on a single machine. And if you're running z/OS 2.1, they've increased logical processors per LPAR to 141. If you do the math, think about that. Just because it's possible doesn't mean it's necessarily a good idea because as good as Prism is, I'm having trouble imagining 12,000 logical processors fighting over the maximum 140 physical processors you can have in a box. It's not going to run well. HyperDispatch will help you out because he can park unused logical processors, but he can't park an entire LPAR. The more LPARs you configure, the more overhead. So it's just a really good idea to keep things as small and simple as possible. Now I want to show you a basic SMF 113 sample on the next slide. If you've never worked with this data before, here's a quick overview of the fields. Now there's many more fields available than I've actually listed here, but I'd say these are a good place to start. I just used my own SAS to create this, but there's many good tools out there in the market available to format the data. So this is some 113 output from a large customer. I dumped a month's worth of data into Excel and just sorted it by cycles per instruction. Very simple. Now, the two samples here are the highest and lowest values by CPI. CPI represents the average number of CPU cycles to complete each instruction. Like RNI, relative nest intensity, the lower the number, the better, with 1 being essentially perfect, as that means the CPU is completing an instruction every single clock cycle without waiting. Now you can see the clear contrast in these examples. The top sample with 16 logical processors takes an average of 7 CPU cycles to complete an instruction. Since this is an EC12, we know that the processor is capable of 5.5 billion cycles per second. Now that effectively means that the CPU is only producing 785 million instructions per second on average, 5.5 billion divided by 7. Now it occurred to me that some of us still use MIPS. This term has kind of fallen out of favor in recent years as millions of instructions per second gave way to other terms like meaningless indicator of processor speed. Now with type 113 measurements, you can scientifically measure your actual MIPS rate. 785 million instructions per second is literally 785 MIPS. If you compare this to the result of the lower sample with a CPI of 1, based on the same 5.5 gigahertz processor, that workload is achieving over 5,000 MIPS. Now, if there's anything your boss is familiar with, it's MIPS. He or she knows that MIPS cost money. Wouldn't it be cool if you could tune your system to increase your MIPS rate and scientifically prove it? Now, there's a good reason to tune. Now, I've saved the best for last. After describing how RNI works, but how most of it can't be controlled, IBM highlights one clear and specific area. They call it software configuration tuning. The full text is on the next slide. I didn't try to paraphrase this because to me it's just written perfectly. Now in this context, software configuration tuning means less is more. Reducing the number of concurrent tasks, such as batch initiators, can improve performance. Now, while I fully believe the science, my time and performance taught me to test. I think a famous US president once said, "Trust but verify." So we did. Here at MVS Solutions, we ran a benchmark on our mainframe. We isolated the machine and used a batch scheduler to steadily submit 1,000 jobs. They were all mixed applications, some CPU and I/O bound, all in the same service class. We first ran them using WLM initiators with no constraints, then ran again using initiators automated with ThrouPut Manager. The automation is designed to check the CPU utilization, the CPU delays, and the performance index of the executing jobs, and adjust the number of active initiators based on these conditions to maximize throughput. Now, to make TM automation truly effective, these checks and adjustments are set to run every 10 seconds, just like a WLM policy adjustment interval. So here's the results. In the first run, WLM started up to 300 initiators, as shown with the pink line. It completed all jobs around 10 hours later. It's a pretty small machine. In the second run, TM automation juggled the initiators up and down, but as you can see, it never exceeded more than 25 initiators, and the entire run finished more than an hour sooner. TM is the blue line. Now, what I found most interesting was actually the green line. This shows the higher rate of job completion with TM automation. By halfway through the benchmark, TM automation had completed 100 jobs more than WLM. And like the line says, it doesn't matter when a job starts, it's when it ends. To me, clearly IBM is right. I think getting the same work done in less time with 25 concurrent address spaces versus 300 concurrent address spaces solidly backs up IBM's advice. Less is more. So to sum up, do yourself a big favor and start looking at your 113s if you're not already. There's a wealth of information in there. Consider I/O buffers, limited application mixes, simple LPAR configurations, and most of all, limit concurrency. It's clear to me that less really is more, and automation is the most effective path to maximize your throughput. Now, please don't go away. I'm going to pass the mic back to CMG and happy to take your questions. And I think Steve is muted.
Yes, I was.
Sorry
Sorry
Steve.
about that.
That's all right, man.
A couple of things, like some of us work on other platforms too. Does this work the same way in other platforms?
Yeah, absolutely. I mean, memory caches are a standard technique that has evolved over the years. They don't all have the same number. For example, like I don't think PCs would have a level 4 cache. Even when we first introduced this concept with the Z10, we didn't have level 4. But the tiering concept is the same throughout any computer.
Okay. And let's see. You mentioned earlier that the CPU speed has actually decreased. Is that correct?
Well, it's not actually decreased. It's a Moore's Law thing. It's not actually even a mainframe thing, but a CMOS processor thing that people way smarter than me have seen coming for many years. Essentially, it seems like we may be actually approaching the end of that line of Moore's Law. So it's not so much that they're slowing down, but the rate of increase. Moore's Law says technically that I can double the number of transistors on an integrated circuit every 18 months, thereby doubling the actual throughput of the CPU. And they are struggling with that with the current CMOS technology. Simply means that we can't rely on, every couple of years, I'll just upgrade my machine, CPU will be twice as fast and life will be good. We actually have to do smart things like automation and finding efficiencies within the system if we want things to continue to run fast, assuming our workload continues to grow.
So, okay, that sounds interesting. The questions come in that say, about back to other platforms. Are there similar performance tools to look at this kind of usage on other platforms? Specifically, I believe that they're talking about the various levels of cache.
Sure. Yeah. Well, I'll tell you, I'm gonna plug the CMG conference here because I'm a mainframe guy, but I am going to be presenting with Claire Cates, Claire Cates from the SAS Institutes. Claire's expertise is in distributed platforms. She is also a recognized expert in memory performance, and I know that she is very well versed in the non-mainframe side of this discussion, and we've submitted a presentation together that we're going to co-present at CMG in San Antonio. So I would say come and listen to Claire, and she can probably give you a much better answer.
That was a good plug.
My pleasure.
Okay, so you've hit on it a couple of times. So this started really with Z10s, or this RNI concept, right?
Yeah.
Okay, so even if I'm not on a Z13, I can still use the same basic performance techniques that you described here, right?
Yeah, basically this type 113 SMF record you created with the CPMF for short, CPU Measurement Facility, that all came about with the Z10. So as long as you're running a Z10 or later, and I believe ZOS 1.9, you can collect this data, absolutely.
Okay, so another question here. A scenario of 100 parallel processes, each running for 20 minutes presently. Would they run faster if 50 parallel processes were running?
So, it's a little broken up there, Steve. Can you just repeat that one?
Yeah, I keep having to turn my head away.
Sorry, man.
So if we have 100 processes running today in 20 minutes, if I cut that to 50 processes, would that cut the overall duration?
I mean, it should. The universal answer, of course, it depends, but absolutely. What we're talking about here is getting the same work done with fewer resources. The problem with having multiple processors in a mainframe, and again, this will apply to any platform, is something that's commonly referred to as the MP effect. When you have more than one processor in a shared machine, we call that multiprocessing, compared with running multiple programs as multiprogramming. Now with multiprocessing, you've got multiple CPUs that are all sharing the work. You've got shared memory and data. You have, as soon as you introduce a second CPU, potential integrity exposure. So if one CPU wants to update the same area of storage as another CPU, that needs to be serialized, and that takes overhead, which is why if you look at any table, such as, say, the SRM constants, you look at the speed of an individual engine on a box. When you add 2, 3, 4 engines to that same box, the individual speed of each engine slows down, even though the total capacity of the machine increases. So what this means is that your single-threaded tasks will actually run slower because they are dependent on the speed of the individual CPU. That was kind of a long answer. I hope that covered it.
Yeah, let me try a little different tack here. I have 100 programs that I'm running simultaneously, right, concurrently.
Okay. Yep.
If I cut that to 50, and they run in 20 minutes, 100 batch processes running the exact same program, they run in 20 minutes. If I cut it to 50 processes, the implication is it should run faster, right?
Yeah, it would if you're overutilized. That's also the factor. That's kind of where that automation piece came in, where you're checking your utilization, right? When you get to 100% utilization and beyond, that's what you have, we call latent demand. That means your CPU is running flat out, and in addition to that, there's work that wants to get done that's not getting done. So by actually limiting the amount of concurrent work, what you're going to do is lower the overall utilization. That's going to improve the speed of the individual programs. That's basically a queuing theory in a nutshell.
Okay, so okay, that makes sense. Somebody's asked the question a little differently too, and if we know we can limit batch initiators, I mean, it's pretty simple to do. We all know how to do that. But how do we limit things like CICS or IMS or what have you on line transactions when the arrival rate varies by second?
Absolutely. It's certainly more difficult with the online, and you never want to turn away a customer. But the idea is there's always a queue. You know, if you have a certain level of demand, there's always a queue somewhere. If the work just comes directly into the system and it's not stopped by reducing initiators or reducing concurrent tasks, the queue is going to be for the CPUs and these memory caches that we talked about. The advice here from IBM that I agree with is queue it outside the machine. So that's the concept of fewer initiators or fewer CICS application-only regions that says, we know you're going to wait anyway, but wait outside the machine. That way the work that's inside the machine is going to run faster. So in a web transaction scenario, and again, I'm not an expert in that area, but I would say your front-end web servers, that would be where you'd want to serialize, slow down the incoming work, essentially based on the utilization of the back-end server.
Okay. So let's see, the next question is, should we separate work into smaller LPARs with fewer CPUs?
Oh, absolutely. I mean, I've seen machines with 10 CPUs in them and 30 or 40 LPARs, and each one of them has access to all 10 CPUs. Well, each one of those LPARs, if you give it 10 logical CPUs, it thinks it has 10 CPUs all to itself. And of course, you're multiplying that by 30 LPARs, so you actually have a series of operating systems that thinks there are 300 CPUs in the system. And these all have to be dispatched on and off. And just like the problem with too many processors and the MP effect, too many LPARs is the same thing. You have overhead in serializing these and accounting for all the weights. So yeah, definitely cut down the number of LPARs if you can.
Okay. Is in-ready a good indicator of work impacted by over-allocated CPs?
Number of ready. Oh, we're talking about in-ready versus, yeah.
In-ready versus out-ready, I guess.
Yeah, a lot of these metrics, if you think about it, they used to be used when we counted UIC, which was a universal interval count based on memory contention. And I guess these days we don't think about memory contention because we have so much memory and because it's so cheap. But the concept is similar. This is, kind of thinking about this, that even though I've got a ton in memory, I shouldn't just throw it all in there. I really should hold back. Is in-ready a good measurement? I'd say it's one. Kind of the idea that I would get at here is the 113 gives you more information. It's not like you're going to stop using your type 70s. You still want to see CPU busy and CPU delay and all that kind of good stuff. But the 113 data can augment that, where you can correlate certain things. Say, well, when I see this type of delay and I see this level of concurrency, how many address spaces was I running at that time? What was the relative delay of those address spaces at that time? Where you can really optimize your throughput. But that's kind of hard to do manually. That's why I get back to the automation argument, because utilization and the demand changes all the time.
Okay. So this next question kind of goes back to the 100 versus 50 processes, okay? Mm-hmm. If I have process 1, which is one program, and I'm running it 100 times concurrently, and I have process 2, which is a different program, and I'm running it also 100 times, is it best to wait for process 1, all the 100 process 1s to finish first, before I start process 2?
If you are, I'm trying to think about this. If you are at full utilization from running process 1, then I would say yes. And one of the things most of us know in this business of performance and capacity is that the term multitasking can be a bit misleading. I mean, at its very basic level, a CPU is nothing more than a series of switches, gates, for people to get down to the physics level, that can really only do one thing at a time. Now, there's all kinds of wonderful enhancements to allow work to be done in parallel. The SMT enhancement, for example, in the Z13 is very, very useful. I mentioned that a CPU would wait if your instruction wasn't ready. Well, this enhancement allows it to do something else. You can have two instructions in the pipeline. But I would still argue that if you're at maximum utilization and you're just achieving the throughput that you need with process 1, I would complete that. Certainly, I would argue that in the case of batch because, you know, as shown with our benchmark, it doesn't help you to have all these jobs running. Your business is dependent on when did they finish, when did they get done. So the more you can get done, it's not just a throughput thing, it's a risk thing. If you have a bends and need to restart and you don't have time to do that, right? So I'm for getting the work done. Of course, using the maximum utilization of the machine.
Okay. Yeah, get application developers to agree to that.
Yeah. Yeah,
So
that can be fun.
Yeah. Let's take that one step farther. If the two different processes, and I'm running 100 of each parallel, if the data access patterns are such that they're segregated, right? So that process 1 is going after database A and process 2 is going after database B. Is it still best to kind of wait for the first set to finish, or?
Well, as long as you're not overutilized, those you could run in parallel because they're each going to use their own local level 1 and level 2 caches. But again, it's a question of utilization.
Okay. Well, it looks like that has exhausted the questions, John.
That's okay. I had fun. Any others? Take an email.
Here comes another.
Okay.
So this is more of a comment, but I would be interested in your response to this. So it sounds like pinning a CPU to one task is best.
So I didn't hear the first word.
Okay, so it sounds like pinning one.
Pinning it.
Yeah, pinning one CPU to one task is best.
Yeah, I mean, in theory, again, taking into account that these are really powerful CPUs, and you want to look at your utilization. If that single task is only driving the CPU up to 50% busy, then clearly that CPU can handle more work. So you would throw more at it. It's kind of the age-old debate of fewer faster versus more slower. And by that I mean fewer processors that are faster versus more processors that are slower in parallel. I've had this discussion with Kathy Walsh, and she says, you know, fewer faster almost always wins. But, you know, you do have to put in the it depends on your workload caveat. The example you gave of two completely diverse workloads that have no relationship whatsoever, there wouldn't be any reason why you wouldn't want to run those in two parallel processes.
I guess the same CP.
The same.
Or
Okay.
two
No, you would run them separate. Like that would be a case where you're better off with two CPUs, even though they might not be as fast, than a single faster CPU, because it's going to be trading the data out. You're going to have to flush all those cache lines every time it switches.
Yeah, that I believe that's where they were trying to lead to, is how does the cache flush work?
Yeah, there's actually an argument in that case where you're running diverse workloads to run them in two processors, even though if they're not as fast, because each processor will have its own dedicated level 1, level 2 cache. And the idea is you want to flush those as least frequently as possible.
Okay.
I'm good.
One more.
Oh, okay. No problem.
So this comes from a throughput manager customer.
Oh,
And,
okay.
He's asking, should this function already be available to him?
Shameless plug, yeah.
Well, I believe, you know, in your slide where you said where you used TM to throttle to 25 instead of letting it go to 300.
Right. Yes.
Processes, right?
Yes. The short answer, yes. If you're running ThruPut Manager automation, which is our latest release, you do have that functionality.
So that sounds like it needs to make a call.
We will take the call. Well, I would say if there's any other questions, you know, feel free to email. Happy to write back.
Here's actually one more that I think is pretty interesting to the group.
Sure.
Is there any way in the like the SMF 113s or anywhere else where you can separate the data and instruction caches?
Separate that. Well, they are architecturally. So level 1 and level 2, for example, level 1 is separated into 96K for instruction and 128K for data. That's in Z13. They're a little bit smaller. The EC12. Z13 level 2 is 2 meg and 2 meg. Whereas that was E13. EC12, it's 1 and 1. But they are architecturally separate already. In previous designs, they were mixed, and the engineers found that it was more efficient to actually separate those. But the question I believe you're asking is, does the 113 show that? And the honest answer is I don't know. So I don't want to say for certain. I do know there are many more fields than I've touched on here. I do know, for example, that you get the total instruction count as well as the total cycle count, which is where the average cycles per instruction comes from. But that being separated into which ones are for data and which ones for instructions, I'm not 100% certain. So I would say, if we know who asked that question, get that to me, and I will check that out.
Yeah, we have it in the log. So okay.
Excellent.
Now back to Throughput Manager for a second here.
Okay.
Does Throughput Manager only limit initiators, or does it somehow limit the ready queue inside ZOS?
It does both, actually. So it will dynamically control the initiators, as I talked about here, based on utilization of the various LPARs, so you kind of get things nicely balanced and not overutilized that way. But also within the input queue, Throughput Manager integrates very tightly with JES2. So long and short of it is, we analyze every job that's submitted. We take all of that work, we put it into a single queue, and then based on the importance of the workload, the urgency, and other factors like the utilization and so on, we decide when a job should run. The queue is ordered by urgency of jobs, so first of all, the first job to start is always the most important. We mentioned that. But yes, it actually does control when jobs are selected as well. And that is automated, but you also have manual controls over that if you want to limit certain workloads.
Okay. Next question is there a utility that you know of that will show the topography of the CPs on the books?
The topography, a utility. I'm not sure about a utility. I mean, first of all, IBM keeps changing names just to keep us on our toes. So they were called books up until the Z13. Now we call them drawers. I basically go to the documentation, you know, the reference manuals and the red books and so on. I do know if you're using ZPCR, which you should be using for capacity planning your machine, that internally has knowledge of all the layout and will take these things into account. But if you're talking about a piece of software that would show that, I am not aware.
Yeah, I think that would be I mean, you can get a physical layout by just looking at the hardware manual, right?
Yeah, exactly. That's where, I mean, these diagrams just came from the red books, and that will show you. But I guess the question is, you know, can I plug a piece of software into the machine and it'll tell me? I don't believe so.
Okay, this question, this person says, what he's taken away is that look for the knee in your process control, look for the knee, and I assume the curve of your process control switching, and tune your concurrency to try and keep the PCS under the beginning of the knee. Would you agree? Does that make sense?
Yeah, that's exactly what we're talking about here. You know, managing that knee of the curve. I mean, when I say limit, well, when IBM says limit, and I agree, we're not saying hold your CPU back at 50% or anything. Obviously, you want to get the most out of your investment. But this is what that question is referring to is, again, essentially a queuing theory thing. That queuing is not linear. And by that, I mean it's not a straight line. At 10, 20, 30, 40% utilization, your throughput or response time is still going to be very, very good. Even though it's, you know, from 20 to 40, you've doubled your work, but your response time or throughput will not have gone up significantly. But if you double it, or even if you move from, you know, 95 to 98%, that's only a 3% increase, but your response time or throughput will increase exponentially. That's where you're getting into the knee of the curve. So yes, the comment is absolutely correct.
Okay, the next question. Does Throughput Manager work with JES 3?
It does not, but we do have a migration tool, and I know that as soon as IBM is ready to pull the plug on that, not that they're going to or anything, but and I don't work for IBM, so definitely don't take my words for that, but I know there are very few JES3 customers out there, and we'd be happy to work with them if they want to convert to JES2.
Okay, John, I believe that's all.
Cool.
Just for everybody's information, we have recorded this, so it will be available on our on the CMG website in the next few days. And if you have any more questions, John, do you have an email address that they can email you a question to?
Yeah, absolutely. Just slide up here at the bottom of the screen there, jbaker@mvssol.com.
Okay. Thanks, John, and thank everybody for attending, and we'll see you in San Antonio.
Thanks, Steve.